So we will discuss gravitational potential as the amount of work done. Let us define this. What do we call as the gravitational potential? And then we will find the value. So we define gravitational potential as the amount of work done in moving a unit mass, from infinity to a point in the gravitational field. To a point in the gravitational field. Okay. So this we call as the gravitational potential. Again, it has a similar significance as with the electric potential. The significance remains the same. It's the same significance. You can use that electric potential concept over here. So as we define electric potential as the amount of work done in moving a unit positive charge from infinity to a point. So in the similar way, we have the gravitational potential. So let us find out the value of the gravitational potential. What is the amount of work done? So here, as you can see, if you want to bring a charge a mass from infinity to any point in the gravitational field, so we do not need to do any work. We do not need to apply any amount of force. Suppose we bring this mass, we are bringing this mass m from infinity. If we bring this mass from infinity to a point in the gravitational field, let us say we bring it over here. So this is at a distance r from the center. So let us assume its distance from the center to be r. This is r, and we are bringing it from infinity. So the gravitational potential at this point, there is a derivation, but we are not going into the depth of the derivation. I will directly give you the formula for the gravitational potential. So the gravitational potential at this point is given by negative gm over r. Okay. Negative gm over r. Is it correct? So we define this gravitational potential as this minus of gm over just 1 minute. Gravitational potential. Okay. So this is gravitational potential minus gm by r squared. We call this as the gravitational potential at any point. So similarly, if you want to find out, this is the gravitational potential at any point minus gm by r squared, it's always negative. That means no work is done in bringing a mass from infinity to a point in the gravitational field. There will not be any work done. So hence this gravitational potential is negative. In a similar way, we find out the gravitational potential energy. So the gravitational potential is given as, it's also known as gravitational potential. It is given as work done from infinity to a point r per unit mass. So this we call as the gravitational potential. And hence if you find out gravitational potential energy, so the gravitational potential energy is given as mass times of gravitational potential. It's given as mass times of that gravitational potential. Okay. So depending on this concept, we'll move further. Just one. Yeah, gravitational potential. I'm just letting you know the formula. Is it r squared or is it r? That's what I'm looking for. Mg. Okay, let's derive this. Yeah, gravitational potential, it's defined as minus Gm over R. This is also not capital R, this is small r. We have minus Gm over R. So the gravitational potential at any point P would be taken as minus Gm by R, and gravitational potential energy would be given as mgh, or it will be V times, since it is, if you want to find out the gravitational potential energy, so the gravitational potential energy would be given by mass times the gravitational potential. Okay. So mass times gravitational potential will give us the gravitational potential energy of that point. Okay. So now we can move on to the questions.
Yes, sir.
Okay. Another thing, since we have heard about the acceleration due to gravity, so acceleration due to gravity is given by Gm over R squared. Right. This is acceleration due to gravity, Gm over R squared, and we can also denote this as force per unit mass. Okay. So force per unit mass is also called as, this is we also call as acceleration due to gravity, or there is another term for this. That term is gravitational field strength. So if you are talking of gravitational field strength, so gravitational field strength means gravitational potential energy. So acceleration due to gravity. This we call gravitational field strength. So let's try to find out the value of, do the questions which are related to this. We will also discuss about the escape velocity and motions. So I think this was the question. Okay. A body of mass m is taken from Earth's surface to the height h equal to twice the radius of Earth. The increase in potential energy will be. So what will be the increase in potential energy? So they have given G as acceleration due to gravity on the surface of Earth. That is G. And we have to find out this. Let's start. So a body of mass m is taken from Earth's surface to a height h equal twice the radius of Earth. So let's say we have this Earth and we take a mass m. Let it have a mass m, and it has been taken to a height from the, okay, twice the radius of the Earth. Here the height h is equal to 2r. That is what given. And we have to find out what? We have the increase in potential energy. So the gravitational potential energy at on the surface of the Earth. If you find out the gravitational potential energy on the surface of the Earth, we find out the gravitational potential energy at this point, and then we find out the increase in potential energy. Okay. So the initial potential energy on the surface of the Earth. Okay. On the surface of the Earth, the gravitational potential is given by Vs. We write it Vs, potential on the surface of Earth, given by minus of Gm over R. Is it correct? So this is the formula of gravitational potential.
Yes, sir.
Okay. Now, if I want to find out the gravitational potential energy on the surface, so I must multiply it by small m. Okay. So the gravitational potential energy on the surface of Earth will be minus of Gmm over R. Right? Remember, the gravitational potential is denoted by potential energy per unit mass. So the potential energy, there is a difference between potential and potential energy. So potential energy will be minus of Gmm over R. Now on the surface, if you multiply this by R in the numerator and denominator, so we get here minus of Gmm over r squared multiply r. So here gm by r square is nothing but g, and hence we can write out minus of gm. This minus of gm by r squared can be written as small g, since the expression which denotes the value of small g is equal to gm over r squared. So we can put this value gm over r squared as small g. So this is minus of m, g and r. This is the gravitational potential on the surface of Earth. Okay. Now we will find out the gravitational potential at a height h equal to 2r. Okay. So can you find out the gravitational potential at this point? Remember, we are measuring all the distances from the center of Earth. Okay. So can you find out and then find out the difference of potential energy? So the difference of potential energy will be final minus initial, and hence you will get the increase in potential energy. Okay. So this is on the surface. Then we find out the gravitational potential energy at a height h. So let's say we find out here. First we say potential at a height h will be equal to minus of gm over, here r is the distance from the center. So from center it will have a distance equal to 3r. This will be the distance. So we have the formula minus gm over 3r, and again multiply by r, divide by r. So you get this as minus of gm over r squared, and here r by 3. Okay. So gm over r squared is nothing but g, and hence we can put here v at height h will be equal to minus of g into r by 3. This is potential, and hence the potential energy at height h will be mass multiplied by this. Remember, here we have done the potential energy will be mass multiplied by potential. So we have minus of mgr by 3. Okay. Now we'll find the increase in potential energy will be final minus initial. So we have delta potential energy, change in potential energy, as final minus initial. So it would be equal to minus of, it would be equal to minus of mgr by 3, and initial value, this is the final value, and initial value will be minus minus, it will become plus mgr. Okay. So what should be the change of potential energy then? Which option should we choose?
Option 3.
Yeah, now it's option 3, 2 by 3 mgr. So I hope you have understood how to find out the gravitational potential and then the potential energy.
Yes, sir.
Okay. So it's pretty simple. See, we cannot measure the gravitational potential or any potential, exact value of potential cannot be measured, right? But if you measure the gravitational potential or any potential as a difference, so it can be measured. So that's why we always measure the gravitational potential difference. Okay, so this one we have done. Okay, now see this one. Two particles of equal mass m move in a circle of radius r under the action of their mutual gravitational attraction. The speed of each particle will be. So what will be the speed of each particle? Okay. So how we are going to find out their speed? Which concept is to be utilized? See, there is, if they are moving in a circle, so there is a concept that we can utilize. The gravitational force should be equal to the gravitational force which is binding them. It should provide them the necessary centripetal forces. Okay. So the necessary centripetal force of any of the mass, you can consider any of the mass, and its necessary centripetal force which is required that necessary centripetal force will be provided by the gravitational force which act between them. So let's apply that and see. If we have two masses, the masses are m, move in a circle of radius r. So to move in a circle of radius r, they require a force towards the center, and that force would be given by gmm or gm squared over r squared. They also require a centripetal force. The centripetal force which is required will be given by mv squared by r. So our target is we want to find out the velocity. So what should be the velocity here? If we equate them, we will get the velocity. We get here gm squared by r squared should be equal to mv squared by r. So r and r gets cancelled. M and 1 of the m cancel. So the value of v is under root gm by r. Right? So which option should be correct?
Option 3.
Option 3. Now, any doubts?
No, sir.
No. Okay, so I think you should also try to do this question. Let's try to do this question. The time period of a satellite of Earth is 24 hours. If the separation between the Earth and the satellite is decreased to 1/4 of the previous value, then its new time period will be. Okay. So which concept is to be utilized here?
T square is directly proportional to r cube.
Yeah, we will be utilizing here t square proportional to r cube. So start solving and tell here. I'm also solving here side by side. Till then you also take your paper, solve it out and see if you are able to get it. So original time period is given. Original time period we take as t, which is 24 hours. Original distance we take as r. So radius we take as r. This is original. Final time period we want to find out. T final we want to find out. And final radius, our r is equal to r by 4. The separation between the Earth and satellite is decreased to 1/4 of the previous value. So now the r is r by 4. Okay. So t squared proportional to r cube. T square equals to k times of r cube. Here you have again tf squared equals k times of r by 4 cube. T is 24. We get here 24 squared equals k and k cancel. So you have 64 r cube over r cube. And here you have ts squared f. So r squared, r cube cancels, and hence 24 by 24 divided by 64 would be equal to t squared. So t would be equal to 24 over 8. Are you getting correct?
Sir, I got T2 is equal to 3.
You are getting 3. Decreased to 1/4 of its previous value. So if you are getting 3, but 3 is nowhere in, oh yeah, here we have 3. Option 4, 3 hours. Yes, if you divide this 24 by 8, we get 3 hours. So the new time period would be 3 hours.
Yes, sir.
Okay. So I think now you are able to get these questions. Let the next one. Let's see this one. If the gravitational field in the space is given by minus k over r cube, taking the reference point to be at r equal to 2 centimeter, with gravitational potential V equal to 10 joule per kilogram. Find the gravitational potential at R equals to 3 centimeter in SI unit. So it's again pretty simple one. Okay. See, there are two methods. Either you find out first the value of K and then use that value of K to find the value of V at next unit. K is given here. K is given as 6 joule centimeter per kilogram. So the gravitational field in space, the gravitational field means the value of G. That's what we call as the okay. So we have the gravitational field. Let the gravitational field be denoted by symbol okay. So how to solve about? How to find out the gravitational field?
I'm not sure, sir.
Not sure. Okay. See the gravitational field in the space. The gravitational fields, when you are finding the field, if you have heard about the electric field, so electric field is given by force per unit charge. Okay. In the similar way, the gravitational field at any point, gravitational field would be given as force per unit mass, and this must be equal to Gm over r squared. So whatever it comes, but the gravitational field in space has been given by this value. So you know it should have the unit force per unit mass, and this gravitational field is given by k minus k over r cube. Okay. So some point in space, this gravitational field is given as minus k by r cube, this, r squared. This is the gravitational field. Taking the reference point to be at r equal to 2 centimeter. So if you put here r equals to 2, the gravitational potential V is given as 10 joule per kilogram. Find the gravitational potential at r equal to 3. So you have to find gravitational potential at V at r equal to 3. This is V at r equals to 2. This you have to find V at r equal to 3 centimeter. Okay, so you have an expression for gravitational field, and hence if you want to find out the work done per unit, if you want to find out the gravitational potential, okay, so the gravitational potential is given by work done, and work is done against the gravitational field. So you will take the gravitational field multiplied by okay. So the gravitational field, let's make the symbol as what symbol shall we take the gravitational field? Let us take it as the symbol E only. Okay, let's take the symbol EG, which we mean that a gravitational field at any point. So if you have the gravitational field given by minus k by r cube, then the work done. First of all, we will find out the force. Force will be given by gravitational force would be given by m multiply gravitational field. and hence the work done would be given by M multiply E multiply dr. So this would be the amount of work done at any point. And if you divide this by mass, you will be getting your gravitational potential. So you have gravitational potential equals to M E dr over M. So M and M cancel. You have the gravitational potential given by E dr. Okay. Now we can find out the potential at any point. So if we integrate this, we'll find an expression for gravitational potential, and hence we can use this expression to find out the potential, to keep the value of potential over here. Okay. So let us try to find out this. So gravitational potential at any point would be the gravitational potential. It will come out as a function k over r squared. Okay. Now the gravitational potential here is given as 10. Let's say value of k is given here. So okay, if you integrate this, you have r, this one is r squared multiplied dr. So if you integrate this is r squared only. Yes. So if you integrate it, you will get here something minus k over r as the function of gravitational potential. So taking this as the reference point, we have at this point we have the gravitational potential V given as 10. This gravitational potential as 10 joule per kilogram. So we put it as 10 joule per kilogram when R equals to 2. If you have R equals to 2, this is the gravitational potential. Then we need to find out the gravitational potential when R is equal to 3. K is given 10. Okay, let's see, it's 10 over. Okay. So this is, let this is your V1 equals to 10. And now we want to find out V2. This is at, this is what we want to find out, and its value is now dependent on minus of k over r. It's inversely proportional to r. So V1 was equal to k over 2, and this is V2 which is equal to k over r, which is 3. So if you divide V1 and V2, we get here 10 over V2 equals to, this was your 1 by 2, and 1 by 2 divided by 1 by 3. So you get 10 by V2 should be equal to 3 by 2, and hence V2 should be equal to 20 by 3, right? So 20 by 3, and if you see 20 by 3, it's not here anywhere. Value of k is given 6. Okay, let's see this question, right? I'll see this question, what this gravitational field, and tell you in the next class. You can see the next question.
Okay, sir.
Okay, can you give any ideas? Anyone if knows? Reference point R equals to 2 centimeter. Okay, we'll see this in the next class. If you can solve it right now as a part, you can also try it as homework. Okay, try it out as homework. Let's see if you are able to do it. Value of key. Okay. Next one. at a certain depth d below the surface of Earth, value of acceleration due to gravity becomes 4 times that of its value at a height 3r above the Earth's surface, where r is the radius of Earth. So the depth d is equal to. So we will use both the expressions for acceleration due to gravity at height and acceleration due to gravity at depth. Let's see. So for height, we use the formula g dash equals g times of 1 plus h by r power minus 2, and this is equal to g dash at a depth which is g times of 1 minus d by r. Now both of them, they are equal, and hence we have to find out the value of h and d. So it says at a certain depth d below the surface of Earth, 4 times, okay. So the acceleration due to gravity below the surface, it becomes 4 times of this. So whatever this value you are getting, if you multiply this by 4, this will be equal to the acceleration due to gravity at a depth d. Okay. Here we have to put the value of h as 3r, putting the value of h as 3r and then multiplying it by 4. So this is g dash at a height h. G dash at a height h will be equal to g times of 1 plus 3 whole power minus 2. This will be equal to g multiply 4 power minus 2 and hence g over 16. So this is g dash of h is equal to g by 16 at a certain height. If you multiply this by 4, so it would be equal to g dash at a depth d. So equating it to g dash at g equals to 1 minus d by r. If you equate, now we can find out the value of d. G and g, from both of them, they cancel each other, and hence you have from these two expressions we get here 1 by 4 equal 1 minus d by r. So transposing the terms, we get here d by r equals 1 minus 1 by 4. So d is equal to 3 by 4 times of radius of Earth. Okay. And radius of Earth is 6,400. So what should be the answer? Yes, can you find out the answer now?
Is it 4,800?
Okay, so let's check it. You have 0.75 multiply with 6400. Yeah, it's 4,800 kilometers. Okay. So today we have got stuck with one of the questions. Just you also try to do that question. Do not try to Google up. Try to understand the concept of gravitational potential, okay, and gravitational field. Right?
Okay,
There are
sir.
not much questions on gravitational field. This was the only one which I incurred about the gravitational field. Okay. So bye everyone. Good night. We'll see again in the next class.
Thank you, sir.
You are